This presentation is a control theoretic re-examination of the all-digital phased lock loop presented by Liming Xu and co-authors for graphic digitizer applications. The goal is to show how the published prototype-based design method works, where its modeling assumptions are incomplete, and how a more direct design approach can better guarantee the desired transient performance. The talk is organized in 4 parts: motivation and project scope, the ADPLL as a unity feedback control system, analysis of the author's design approach, and a better design approach based on the actual closed-loop transfer function. The central idea is that once the ADPLL is written as a standard feedback loop, familiar control tools such as pole zero mapping and Routh Hurwitz analysis become directly applicable. Graphic digitizers require a high-frequency pixel clock that remains locked to the low-frequency horizontal synchronization pulse, even though the reference pulse is absent for most of each video line. In a conventional analog PLL, that sparse reference can allow the oscillator frequency to drift during the blind interval, which is exactly the practical problem this ADPLL architecture was designed to mitigate. The paper's solution is a digital loop built around a flying adder digital control oscillator and a software-implemented adaptive filter giving fast digital frequency updates and eliminating the need for off-chip passive RC loop filter components. This project has 3 objectives. A, model the ADPLL in both the continuous time and discrete time domains. B, replicate the paper's design flow numerically. And C, critically evaluate the resulting stability and transient response claims. The reference case is the XVGA mode used in the paper, where the sampling rate is approximately 60.023 kilohertz and the target lock time is 1 millisecond with no more than 1 overshoot, which the authors associate with a damping ratio of 0.707. Later in the talk, that prototype assumption will be revisited because the implemented loop contains a zero and therefore does not behave exactly like a pure second-order prototype. The ADPLL can be reframed as a standard unity feedback control system with a phase detector, software filter, digital control oscillator, and phase feedback path. The software filter acts as a PI controller in the form of a proportional term plus a discrete time integrator, while the DCO acts as a digital integrator with a 1-sample delay. This interpretation is important because it lets the loop be analyzed using standard feedback control methods rather than only with application-specific PLL intuition. By lumping the controller and plant gains into the parameters K1 and K2, the open loop and closed loop transfer functions can be written in compact algebraic form. The closed loop transfer function has a second-order denominator and a first-order numerator, which means the implemented system includes a 0 in addition to its poles. That 0 becomes central later because it shifts the actual transient response away from what a pure 2-pole prototype would predict. The author's design method begins with a textbook second-order prototype in the continuous time domain, defined by the damping ratio, zeta, and natural frequency, omega n. Those analog poles are then mapped into the z-plane using z equals e to the s t sub s, and the resulting discrete time pole locations are used to solve for the loop parameters. This is a reasonable first design step, but it matches only the denominator dynamics directly. The numerator 0 in the realizable loop still changes the final step response. Using the XVGA design targets, as shown on the left-hand side, the paper computes omega sub n equals 5657.71 radians per second, and then derives K1 equals 0.1248 and K2 equals 0.0083 from the mapped pole equations. Substituting those values into the implemented transfer function yields the final closed loop model presented in the case study. The paper also reports simple independent jury-style bounds on the gains, namely K1 between 0 and 2 and K2 between 0 and 4 as its stability limits for the ADPLL architecture. In the following section, I will replicate the author's design and confirm their results. To confirm the stability of the system, the exact discrete time characteristic equation is transformed into the R domain using the bilinear substitution z equals r plus 1 divided by r minus 1, which maps the unit circle to the left half plane. After clearing denominators and collecting terms, the transformed characteristic equation becomes K2 r squared plus 2K1 r plus 4 minus 2K1 minus K2 equals 0. Applying the Routh Hurwitz criterion to the R domain, characteristic equation derived in the previous slide shows that the stable region requires 3 conditions as shown in bullet number 3. An equivalent method to reproduce the paper's gain values is to work directly in the Z domain by computing the discrete pole radius and angle from zeta, omega sub n, and t sub s, expanding the target discrete characteristic polynomial and matching it to the denominator of the implemented ADPLL again yields K1 equals 0.1248 and K2 equals 0.0083. This matches the author's derived solution. Due to the fact the prototype dynamic model did not include a 0, and in order to meet the target design requirements outlined in the paper, we will need to tune the pole-matched discrete model H of Z. Using MATLAB PID tuner tool, the discrete time model gains were increased from baseline to K1 equals 0.189 and K2 equals 0.0102, thus improving the transient response and meeting all time domain design requirements. In the resulting comparison, shown on the left-hand side figure, the baseline design shows about 22% overshoot, while the tune model reaches the 16% overshoot target with roughly 1 millisecond lock time. This slide serves to verify the new gain values are well within the corrected Routh Hurwitz stability conditions. In the previous section, I focused on replicating the original work and verifying the results. In the next section, I will briefly describe what I believe is a better design approach using modern discrete time control theory. Working through the prototype mapping path suggests a cleaner alternative. Start from the actual continuous time closed loop transfer function and design the transient behavior there first. In that exact continuous time model, the denominator still looks second order, but the numerator contains a zero that is inherent to the implemented loop. The practical benefit of starting from the true continuous time closed transfer function is that the analog design can be made consistent with the realizable loop before discretization, reducing the need for later tuning. The paper itself notes that the prototype response and the implemented ADPLL response are, quote, noticeably different as expected, end quote. This is an important admission in the original case study. The side-by-side comparison shows that once the actual closed-loop transfer function is used consistently, the continuous time and discrete time responses align with the realizable loop model rather than with the simplified prototype. This work reproduced the original ADPLL architecture and confirmed the paper provides a useful and practical mixed signal control structure for recovering a pixel clock from horizontal synchronization. The main control theoretic findings are that the implemented loop includes a zero that changes its transient response relative to a pure second-order prototype, and that the true parametric stability region also requires the coupled condition. A better design workflow is therefore to analyze the actual closed-loop transfer function, derive gains from the realizable model, and then discretize systematically using Tustin or all-zero matching techniques rather than relying only on a prototype that does not fully capture the implemented loop. Thank you for listening.